Okay, great. Thank you everyone for allowing me to present. What I'm going to share with you is an overview of printed electronics. I'll share about the technology in general on printed electronics, the history, kind of where we're at, the market of printed electronics, some of the applications printed electronics is used for, the technologies involved, and where printed electronics, I believe, is going. As Vinay mentioned, I am the president of Sonoplot, and I'll get into a little bit of history about the company as well. But this is really not a presentation specifically about Sonoplot. This is a generalized printed electronics presentation. So let's get into what really is printed electronics. Well, it involves conductive materials on flexible or non-flexible substrates to create circuits and components in the electronics industry. So that's a pretty wide range of applications and a pretty wide overview. And I'll get into some of the specifics here. But the origins came out of the PCB market as the PCB printed circuit boards became more customized and the technology began advancing for laying down the traces. Everybody wanted to go smaller and smaller. And so technologies emerged to get those traces, get the electronic components smaller and smaller, and more adaptable towards different applications. Some of the applications are in electronics, so shrinking electronics like transistors, displays, wearable devices, medical devices, sensors, etc. See, can you guys, there we go. Okay, wait. Okay, so it started, as I had mentioned, within the PCB industry and screen printing technologies. And one of the things that they wanted was the ability to be more flexible. So rapidly iterate on designs, be able to do rapid prototyping, R&D working. And post the 1950s, the inkjet technology started to emerge, primarily for printing. And folks soon found out that they could use that or leverage that same or similar technology for printing electronic materials. And hence the printed electronics revolution started. And there's been quite a few advancements in the printed electronics technologies that I'll get into, as well as the materials being printed with these different types of printers. The market has been growing pretty considerably. As you can imagine, electronics is a massive market, but printing these electronics, when you can get the costs down and with the proliferation of cheap and inexpensive electronics, the market has just exploded. Specifically in the printed electronics market, it's expected to be about 30 billion in about a year and a half. So it's been rapidly expanding. It's really gone from an R&D phase, primarily born out of universities, into commercial development now. There's still quite a bit of new R&D happening though at universities, at company R&D, government R&D facilities, etc., creating new markets for new types of devices, new materials, and new applications for these things. As I mentioned, there's a number of areas of innovation going on in the printed electronics marketplace. One is the materials. So as we've evolved from using standard, say, silver nanoparticle inks, we've now been using gold, we've been using copper. There's a wide range of nanomaterials, also ranging into some of their carbon-based materials like carbon nanotubes and graphene, which offer unique electrical capabilities. The applications have grown quite a bit. There's a large push over the last couple of years into the sensor market. So both IoTs for gas type sensors, as well as diagnostic materials in the healthcare industry. So cheap, inexpensive sensors that can be used out in the field. Um, and then there's been advances in the actual printing technologies themselves. So moving from a standard inkjet process or screen printing process, including even subtractive processes like what would be done in a semiconductor industry, to additional and hybrid printed hybrid technologies. Here's a couple of the main technologies in the printed electronics marketplace. As I mentioned, inkjet was sort of one of the first adapted market or technologies that involves piezo or ultrasonic excitation, where then the droplets of ink or the material are forcibly ejected out of the dispenser and drop down onto the substrate. It's a non-contact. It allows for rapid prototyping. It's a very novel technology or well understood technology, but it has its limitations as far as repeatability, accuracy, feature size, etc. On the other hand, there's screen printing, which is traditionally used for production. So it's typically high volume. When you've already done your design, you've figured out the product, and you want to go into high volume. The downside of screen printing is it's expensive to set up. You need to set up the equipment, and also it's not flexible. Once you have a design, you can't really change that. So it's like a machine shop. Once you machine a part, you can't change it. You have to continue to use that. In between, there is a technology called aerosol. So aerosol technology atomizes the conductive material or the material you're printing into droplets that are then placed down and directed down onto the substrate. A little bit more controlled than inkjet printing, but much more expensive equipment for that technology. Not quite as expensive as screen printing, and yet it does still offer some flexibility in the design, so you can iterate your designs and do different types of designs with the same piece of equipment. But it's an order of magnitude more expensive than, say, the inkjet printing. And then there's technology like Sonoplot, which is really a hybrid technology. So we utilize ultrasonic excitation to create a cavitation in the pipette that we're using as a dispenser. This then gently pumps the material out. That combined with surface tension, where we actually create I have a slide here. Here's a little bit of more detail here of creates a droplet of your material out of the dispenser, and then you can actually draw out your material. And so this allows for a couple of unique capabilities. One is it's not using heat or squeezing the pipette like an inkjet, so it's very gentle. It allows you to use a wide range of materials, so higher viscosities than you would with an inkjet or an aerosol-based technology. Not quite as high as viscosity as you would get in a screen printing application, but it's a higher viscosity than that. And then it prints a wide range of materials. So you don't really have to tune materials like you do in inkjet, where there's specific materials designed to use in an inkjet or an aerosol technology. So, like I said, Sonoplot's technology is on the cost spectrum as a traditional inkjet printer. However, it utilizes some other capabilities, allowing it to get more features or more capabilities than just a traditional inkjet. Some of the applications for printed electronics are the flexible electronics, so things like e-readers, displays, RFID antennas, wearable devices, sensors, etc. Integrating into textiles, as well as monitoring for health, not only on diagnostics, but monitoring different aspects of health, like blood pressure, oxygen, etc. And then a large area of research over the past couple of years has really exploded with sensors. So everything from environmental sensors, IoT, to diagnostics and biosensors. There are some limitations, as I've touched on in the earlier slides for printed electronics. Some of the challenges are with the materials. So you have to specially design materials for the different type of printing technology that you're using, whether that's nanoparticle inks or polymers, or graphene solutions and slurries, carbon nanotubes. You typically have to experiment with the materials. And sometimes those materials are great in an inkjet environment or a printed electronics tool like the microplotter, but they're not great when you move into maybe more of a high throughput system like a screen printing or into a fab. The resolution and precision. So depending on which technology you're using, the resolution is not quite there. That all depends on the type of system you're using, but you can't get down necessarily the feature sizes that you would say in a traditional semiconductor fab environment. And then the scalability. Most of these inkjet and hybrid models and aerosol models are just really not made for high throughput and production. As I had mentioned about our technology in particular, we offer a high resolution and repeatability because we're actually very close to the substrate and we're not forcibly ejecting droplets out to create a feature. We're actually more drawing it out. We're very repeatable. We can get very small. We have apertures of our dispensers down to 1 micron. So depending on the surface chemistry of the ink or the material you're printing and the substrate, you can get very small features. As mentioned, our tool allows you to use a wide range of materials. Because we're not forcibly ejecting droplets, we're more printing it out or pumping it out. We've printed everything from, nanoparticle inks to slurries, polymers. We've even printed glues. We've printed all the way down to stem cells. So it's a very versatile machine, allows you to do a lot of different types of printing. Inkjets in general allow you to print different types of materials as well. They can print conductive materials, resistive materials, insulating materials, etc. And then it's like I said, we're a very controlled environment, so it's not shooting out like an aerosol. We're not shooting out like droplets, but it's not as controlled as say a screen print where those features are really well defined. So it really depends on the spreading of your and the surface chemistry of your materials along with the substrate. So a lot of people do various different experimentation. They'll experiment with different types of inks, different concentrations, different solvents. They'll do surface treatments of the substrates, whether that's say a glass slide or a silicon wafer or a flexible substrate like PDOT, something where they can treat it to make it hydrophobic or hydrophilic, depending on what capabilities they're looking for. Um, Some of the different types of materials I've touched on, everything from conductive inks, which includes silver, copper, there's gold now being used, a wide range, and then there's hybrids as well. For conductive material, there's semiconductor polymers, and these are for often used in conjunction together with dielectric materials as well to create different types of circuits. So you can use these tools and different types of inks to create different electrical capabilities, different types of circuits, whether you're creating transistors or OLEDs or sensor materials where you're printing with microfluidics. You can combine a lot of different technologies in a unique way. Um, what are some of the challenges with polymers? Some of the common ones are PDOT, polyaniline, and others. Um, they can be finicky, so it can be hard to, depending on the technology you're using, it can be hard to get the right mixture with the right solvent for what you're trying to print. And the right electrical capabilities. So for instance, if you're trying to print and get a certain resistive capability or certain conductive capability, it can be difficult because the layers are very thin when you're printing electronics, and especially when you're using materials like this. Adhesion can also be a challenge. So depending on your substrate and if it's flexible, making sure that polymer can adhere and stay adhered can be a challenge. So there's typically a lot of R&D and a lot of experimentation that goes on with this. I mentioned graphene. This is a large area of research going on right now due to the unique capabilities of graphene as well as carbon nanotubes. So carbon-based materials. It's very high conductivity along with the CNTs and provides excellent capabilities as long as you can get them to align properly. So there's some unique capabilities when you're using different printing techniques. We found with the microplotter, as you're printing along and drawing out the line, you can get say the nanotubes or the graphene particles to align in such a way that creates a very unique electrical capability, very highly conductive. It's very flexible and inexpensive. So, graphene and CNTs tend to be quite inexpensive compared to, say, like a gold nanoparticle ink, etc. They're used in a wide range of applications these days, from sensors to storage systems, and a lot of research is going on in this area.
How is the stability? Just a quick question. How is the stability of the graphene ink?
It depends on the ink. So a lot of people, what we're finding, are formulating their own. There are some commercially available graphene inks out there, but a lot of people want to develop their own based upon the electrical capabilities that you're trying to accomplish. Quite stable. You really want to stay away from solvents that are highly volatile. So something like toluene or lower in volatility. The reason being is, all of these technologies use, come in contact with the air. And so as soon as anything in a highly volatile solvent comes in contact with air, it'll dry up and that tends to clog. So inkjets, aerosols tend to have clogging issues. We have less of that because we're actually the meniscus the fluid is in touch with the substrate. So the cavitation within the dispenser, along with the constant wetting of the substrate, reduces it. But if your solvent is very volatile, it still will dry pretty quickly. I've talked about nanotubes and graphene. Their capabilities are quite not well understood, I would say. There's a lot of research going on in this area. Quantum dots is another area that's being used in displays, a lot of display technology. That's a big area of research. There's a paper on our website that you can dig into if you're interested in quantum dot research. But it's the scalability right now. So most of these technologies are being used in R&D and novel applications, haven't quite made it yet to the mainstream semiconductor technologies yet. I mentioned some of the research going on in the area. There's a lot of new materials that are emerging in organics. A lot of research mixing them, so nanoparticles with CNTs and with other materials, mixing them with different types of solvents to try and drive different electrical capabilities. So a lot of research going on in those hybrid materials. Let's talk about the sensors. I mentioned that this is a big area of R&D going on right now. There are quite a few sensors out there, printed electronic sensors, that are in the marketplace, and a number of companies that are in this area. It's growing rapidly, primarily because it's very inexpensive to create these sensors. Traditionally, sensors have been quite expensive, and so you don't want to use them on throwaway type or one-use type areas. But when you're using printed electronics and these new low-cost sensors, now doing out in the field diagnostics or one-time use applications becomes really feasible. Lots of different industry applications that I'll get into in a couple slides here. Um, there's sensors, everything from gas sensors, temperature, pressure, motion, the whole range of sensors into diagnostics with microfluidics. Here's an example of medical applications. So I mentioned biosensors, so real-time health monitoring. Some of our customers have actually even printed onto a very thin tape-like material that then just gets adhered to the skin and then is read magnetically. Diagnostics is a huge area. So as you can imagine, doing testing of blood samples, of saliva samples, of various other samples out in the field where you need to just have a quick and dirty sample and get a reading real quick, where you don't want an expensive machine, is really becoming a lot more commonplace. The portability of these sensors, the low cost, is really driving this marketplace. Packaging is another area that's become quite large. So not even just RFID antennas, but being able to incorporate sensors into smart packaging. So, freshness indicators, things that are, used by the billions out there and can monitor various different capabilities within what you're packaging. This is a large area that has really been growing the last couple of years.
So what they do in packaging means like you mean the RFID tag or the electronic packaging?
RFID is for tracking materials, but then they're building in sensors. So printing sensors onto these packages that allow for oxygen measurements, time of packaging, so that they can track, the freshness. They can track where it was from, how long it's been in the package, these types of things.
Okay.
One of the things that's really interesting being in this industry and having a tool where people are doing a lot of research is we don't actually know what they're doing with the machine. So we know at a high level, but obviously a lot of the research that they're doing is very proprietary and novel, and so we only find out about it after the fact, after they publish a paper, et cetera. And we try and keep up with a lot of that. We've put a lot of the papers that are getting published on our website. There's a lot of searching you can do on Google Scholar in this area as well. But a lot of times we don't know exactly the types of materials that they're using. We don't know exactly what types of designs they're doing. We just know at a high level what they're working on.
Okay.
Some of the other areas for these electronic noses, as mentioned in agriculture, so you can detect ammonia levels for livestock to make sure that there's air quality issues, monitoring for leaks in facilities, especially when there's harmful chemicals involved, outdoor or in-home air quality measuring. A lot of these things where you want to have a lot of different sensors, you want to be able to take lots of different readings. And you don't want expensive equipment. I mentioned screen printing earlier, and I think it's worth touching on. Screen printing is really the most common technology used when you're taking a design from, say, inkjet or our technology or aerosol and trying to go into production. It is ideal for large scale production, and it can do very large numbers. It does have its limitations, though. It's limited on some of the resolutions that you can get down to, precisely depending on the material that you're using. It also requires a high cost investment to create the designs on the gravure machines. But it is currently the most common method of going into high production, high volume production. The other downside too is it has to be on flat materials, and there's a lot of research going into combining, say, printed electronics with 3D structures like MEMS or other structures where you want to have maybe on a lens like a curvature or different types of substrates, textiles, things like that. I just touched on some of these things, the dimensional substrates incorporating with MEMS and lenses, the cost effectiveness of it. It's not really usable in sort of the early phases of design. The precision can be challenging. So where is the future for printed electronics? What are people researching? Where are the advances coming from? There's new and advanced materials. I touched on this earlier. People are not only researching new materials like while graphene and CNTs aren't new materials, they are in the printed electronics industry, and being able to get the properties and be able to print them properly so that you can get the right effects are brand new. Other things like hybrid materials where you're mixing these types of things together is a big area of research. Integrating them multiple different sensors, so adding more capabilities in sensors. So you're not just dealing with, say, an ammonia sensor, you're dealing with oxygen and ammonia and maybe noxious gases and nitrogen and a bunch of different things. So you're combining these technologies into new novel sensors, building them sustainably. So it's expensive to build fabs. As we all know, the semiconductor industry is struggling with trying to be able to build new fabs. So being able to build um, and design these things where you can even do them out in the field, kind of analogous to, say, the 3D printer market, where you can now feasibly build parts out in the field and have smaller production facilities to build parts. The same thing's going on in the printed electronics industry, and then just continuing to drive down the costs. And that's it. That's the overview of printed electronics market. Hopefully I gave you guys a good overview of what some of the technologies there are, what the materials that are being used, where they're being used, hopefully where they're going, and a little bit more about Sonoplot and the machine that you have and its benefits and weaknesses. Are there any questions I can answer?
So you discuss about the applications, future prospects is really nice. So if someone look their career in printed electronics, how they can see, and is there a sufficient market for that person? Because most of those students, they are electrical engineering background. Uh, how they can contribute in the field of printed electronics?
Sure. Yeah. Great question. So the technology, so Sonoplot started about 20 years ago or so, almost 20 years ago. We were a spin out of some research done at the University of Wisconsin-Madison in the materials science department. So we're not too far away from you guys. And at that time, actually, the technology was not developed for printed electronics. The market was very nascent at that time. We developed this technology more for proteomics and research in life sciences. And that market kind of disappeared as DNA arrays became commoditized. Proteomics never really took off. And we found people were using our systems in these novel ways to kind of print new and different types of materials. And one of them was these conductive materials in electronics. And so we started looking at that market. And at that time, printed electronics was really new, was very novel. Not many people were doing it. And it soon blossomed into many universities started different labs, a lot of different research areas. People were applying this technology to different markets. Now what you have is actual production, companies based upon using printed electronics to design their products. And so it's quite a large market. As I mentioned earlier, it's about a $30 billion market in 2020 by 2026. There's a number of commercial entities, so there's many careers available in this marketplace.
How about if you solely talk about the inkjet printing? How is the market of it? In most of your customers, they are mainly from academic, or they are from industries as well?
So I would say the majority of customers are doing rapid prototyping for products or research. And now within that, we do have some customers using our technology for production, low throughput production. We do have one company, Renesys, that's using us for higher volume production. But it's really not ideally suited. They just kind of more legacy got into that. So it's mostly on the R&D. Now, it's definitely, I would say, of the customer base, I would say probably 60% are still at the university level. The remainder are in commercial applications, so companies, but doing research and doing rapid prototyping. So doing product development. We have a lot of companies doing product development. Oftentimes, like we were a spin out of a university, there's a lot of research that leads to company formation. So there's a lot of startups that are using us as well.
So in the product development, what kind of products like 3D printing on the micron scale or uh,
No, these are like the products that I mentioned. Sensors. Sensors are a huge thing. Diagnostics. Doing microfluidic diagnostics. There's still a lot of research going on with antenna design, RFID antennas, printing on various different materials, flexible electronics for incorporating into other products.
okay, good. So your
So there's
system
a lot of product
is
development.
yeah. So your system is the microplotter proto is a hybrid between the inkjet printing and the direct writing, right? So if the micro, what are the advantage features of microplotter over inkjet?
So, yeah, that's correct. We're a hybrid approach. So while we utilize ultrasonics like an inkjet, we're not forcibly ejecting the droplets out. So we're more writing and pumping. The advantages of this are we're able to print higher viscosity materials. So we can print upwards of 450 centiploid in viscosity materials. We don't require specific tuning to our printer, whereas most inkjets require specific tuning. The other is our consumables. The ongoing cost of operating is very low. So our dispensers, the material that's actually holding the material and printing it is one of two materials. One is a borosilicate glass that's like a microneedle, glass microneedle. The other is a ceramic material. These are very low cost materials that you can refurbish the dispensers yourselves at a low cost. And so the ongoing maintenance and ongoing cost of using our systems is low. The other advantage is it is very flexible. It prints a wide range of materials. So as I mentioned earlier, we printed everything from the nanoparticle lengths and polymers all the way through live stem cells because of our gentle nature. We're not creating a lot of shear force by squeezing the pipette like an inkjet or forcibly ejecting these droplets out, or aerosol, creating an aerosol like, say, an Optimec machine. We're actually just more gently pumping them out. So it's a much more gentle process. The other advantage we found, and there's been a paper published on this, is when printing carbon nanotubes, one of the benefits of aligning them is the electrical capability. So if you can have all the nanotubes aligned together, it creates a much better electrical conductor, a very high conductive material. When we found by printing ours and we're drawing them out, it's actually aligning them quite a bit. And so there's been a lot of research in that area for the carbon nanotubes. So these are a couple of the advantages. The downside to our technology is we have to get very close to the substrate. So since we're creating that meniscus and the meniscus of the fluid is touching the substrate, we need to get very close. So probably about 10, 15 microns, 5 to 10 microns to the surface. And then what this means is the substrate needs to be very flat. So our ideal substrates are things like glass, PDOT, um, 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 silicon wafers, things like that.
Yeah. So in the inkjet, are all inkjet a non-contact method? In one of your slide, you said inkjet is non-contact. When you say non-contact means like in very much close proximity to the surface. So if you compare microplotter versus the inkjet, traditional inkjet, uh, how you will say like, which one is more non-contact?
The inkjets are more non-contact because they don't actually have a meniscus of fluid that touches the substrate. They shoot it out, so they can be tens of microns above the surface where we have to be a lot closer. Now we don't our dispenser does not actually touch the surface, but the meniscus of the fluid does. And sometimes, depending on anything from a speck of dust or anything, any irregularities in that substrate, our dispenser can touch down onto the surface, and this is what causes the wear on our dispensers. So our dispensers, if you're using them in an ideal situation, don't wear down or don't break. But as you can imagine, anything that's at I would say most common dispenser sizes are 10, 20, 30, 40 micron in apertures. So when you get down to that small a size scale on any material, whether it's a glass, ceramic, or metal, it's very fragile. And so, it'll tend to break over time or get damaged over time. So that's why we've developed this method where you can easily refurbish the dispensers.
So with inkjet also, do they need a very high surface finish, very nice surface finish polish, or they can do on rough surfaces as well?
Depends on the feature sizes you're trying to accomplish. They can tolerate a little bit rougher surfaces, but ideally they're as flat as possible. They struggle to print over, say, curved surfaces or MEMS. They can't really print over 3D structures. But if there's some irregularity, which like you would get in, say, a textile or paper, sometimes people want to print electronics on, say, a paper. Um, they can handle that a little bit better.
In the inks, you mentioned the viscosity with the microplotter is between 0 to 450 CP. Uh, is there any optimized value for it? Means uh, actually in our lab, uh, we print many different type of materials, and some supplier they whenever they sell the ink, they specifically say that it's a inkjet ink, and the viscosity is between 0 to 450 CP. Is there any optimized value? Means you say, okay, this is the range, but we prefer it's above 200 or 250 is good. Any optimized value for it, or any like wide range between 0 to 450 can be easily printed?
Yeah, you should be able to easily print it. Now, like I said, there's really a couple of main variables that go into printing. One is not just the viscosity, that's one, but the surface chemistry of your substrate and the material. So depending on, contact angle of the material, the surface chemistry of the substrate, how hydrophobic or philic it is, that'll determine how much spreading there is and how much adhesion there is between the material you're printing and the substrate. So there's a lot of experimentation that goes on there. Nothing to do with our printing technology. You don't have to tune anything for it. We can print these wide ranges of material. The third is the solvent. So if you're using a non-aqueous type solvent, you really don't want it to be too volatile, otherwise it'll dry and then everything just clumps or clogs because it's drying too fast. Um, the other factors are how does it cure? So some inks or some materials will cure just after printing by drying. Some heat cure, some UV cure. So that'll depend on the type of material you're printing as well.
Yeah. So sometimes people use the the substrate prep as well, right? Like plasma treatment to
Mhm.
make the better adhesion. Uh, so can we control the hydrophilic and hydrophobic printing? Uh, it all depends on how the substrate is being treated well.
Yeah, that's a main factor for not only adhesion but spreadability. So there's actually a paper on our website about plasma treatment. So you can learn about some of the different types of treatments. So there's spin coating, plasma treatments, various different materials that you can use to treat the substrate to get the type of properties you're looking for.
So just one very foolish question, like can we print water on a glass slide from your microplotter, because that also fall in the range of 0 to 450 CP, right?
Of course, yeah, yeah. That's actually a common thing to use for testing, is just use some food coloring and water to test printing.
Okay. In your microplotter, we use the capillary, right? And
Hmm.
actually, we just purchased this printer, so we are also trying to improve our skills, doing more artwork with the printer. So, how to clean the capillary? Because capillary uses the piezoelectricity, right? And if, like, is it true that one capillary is used for one material and it cannot be reused for another material?
No,
Is there a
you
way
can
we can
use,
clean it? Yeah.
yeah, you can clean it. So we accept for design files, we accept DXF file format. And in DXF file formats, you have different layers you can specify. And
Okay.
you can specify those layers as different materials. And when you do that, you can also, when you set up the print job, you tell it where each material is. So if you have, say, three different materials, you specify where on the platen it is. Oftentimes, people use 365 well plates to store their materials. You can also specify rinse or waste wells. So you can automatically specify a protocol for printing material, emptying it out, cleaning it in a solution or a solvent, going and picking up a new material, printing that, et cetera, et cetera. So you can automate that in the software.
Can it be cleaned with IPA, isopropyl alcohol, or acetone? Because is the material plastic, the capillary needle,
No,
the
it's
micro
a
needle?
borosilicate glass. So we have two materials, a borosilicate glass and we have a ceramic material. So the ceramic material is much more durable. It's a harder material. Um, Typically, the ceramic material, though, due to ceramic properties, it's a little bit more porous. It's harder to clean. So typically, those you want to just use with the same type of material. The borosilicate glass you can clean. The type of solvent or cleaner that you want to use will depend on the material that you're printing. So you can
How
experiment
about
with a
for
few different
silver?
types.
How about for, because silver is the most popular with the printing techniques, right?
Hmm.
So and the most of silver inks, they are dissolved in IPA and the acetone, right? So
Hmm.
can the capillary be clean with the acetone or IPA? Means like just fill after you print, you want to clean the capillary, so just fill it with IPA and then release it. It clean the capillary. Is it possible?
Hmm. Yep. Yeah, you can do that. I mean, you would want to experiment and just test it to make sure it's cleaning enough. And you can also specify a cleaning protocol. So maybe it takes two or three cleaning or rinse cycles to be able to clean it.
Okay. So have you guys tried it? Means like if yes, how did you try? Have you
Yeah,
played with
it's
it?
all experimentation. I mean, we've tried hundreds and hundreds of different types of inks. We stay ink or material agnostic, so we don't recommend a specific one. We know certain ones have worked well. We know certain ones that we've used, but we try and stay away from specifically recommending a specific ink, primarily because they each have their own different characteristics and qualities, and it really depends on your application, what you're trying to accomplish. So, depending on the electrical capabilities and other capabilities you're looking for. So, we certainly have partners that we've worked with, like Sigma Aldrich and UT Dots, actually based down out of Champaign down there. There's a number of companies that provide different types of inks and materials. But oftentimes, yeah, we get customers that want us to try an ink or experiment with something. So we've tried a wide range of things.
So in the printing, how to control the alignment? Is it means like, because if we want to print multiple material, let's say like, you are printing four rectangles side by side, right? And
Mhm,
they all are of different material. Can we do
mhm.
with the inkjet printing or with the microplotter?
Sure, yeah, you would just have it in your DXF, your CAD file. You would design the four squares or the four features, specify the different materials, and then you would just um, set it up in the software and print it. Yep, you can do that.
Yeah. With the microplotter, have you ever draw a nice drawing, colorful drawing, just to show the capabilities of the alignment? Uh,
We have not that I'm aware. I mean, we definitely done designs with different materials and things like that. There's also the onboard camera. So if you see the videos that are on our website, um, you can see us printing. There's and you've seen it on your system. There's a camera there and a camera window, so you can see the actual printing. You can align to interstitials. So if you need to say you need to print a material and then take it to a UV curing station or a heat plate to cure and then bring it back and then print another layer, you can align to those interstitials.
mhm, mhm. Yeah. Yes, actually, most of our projects, they are dependent on the alignment. So
Hmm.
uh, I have to print four materials to make the OECT structure, that is the transistor, and that has the metal, uh, dielectric, and the semiconductor. So they all are of different materials. So and actually, my students, they are also learning this tool, and it's quite exciting. uh, but we are like, taking our baby steps to learn
Hmm.
the system. And the alignment is one thing which we are really working on to find that, like, let's say I have four squares, and
Hmm.
they are like, just covering one circular area. Around a circle there are four squares, and we have to draw a fifth square which are touching all those four squares. You see my point?
Hmm. Hmm.
So how to make the center one so that it exactly touch the boundary of it. So we are
Yeah, I mean,
playing
we'd
with
have to
that
look at the
structure.
design and figure that out. Yep.
Yes, it's more like an engineering work as well, right? So what happened that we uh, try to draw a rectangle with the microplotter in the CAD file. We
Hmm.
gave that design, and it plotted only the boundaries of it.
Yeah, it depends on how your design is done in the CAD tool.
Yeah.
So if you're trying to print a filled square, you need to raster it. If you have only done the outside, and it depends on how your design is
Yeah,
done
yeah.
in the
Actually, in
CAD
the
tool.
CAD, because the way it looks in the CAD, it's very much different, because this is more like a engineering you have to play. So first day we gave just the rectangle and fill with the rectangle. CAD can easily
Hmm.
do it. So, and one student, he tried to print, and then he said, "Oh, it printed only the boundary." So I said, "Oh,
Mm,
okay." So
okay.
now we have to
Yeah.
go into the spiral to fill the square. So.
Yeah. And Steve can help you. I mean, you've worked with Steve. He can help you
Mhm, mhm.
on things like that. Yeah.
Yeah, so the same thing apply to the circular structures as well. So whenever we print, it prefer mainly the lines horizontal and means like X and Y direction, or it can print the circular patterns as well. Can we print
Circular
circular
patterns.
patterns? Okay. So in
Yep.
the circular pattern, how we have to do like is spiral in the circles?
Yeah, you can. I mean, it depends on the design you're trying to do. If you're just trying to do a spiral, then you can just do the spiral. I mean, that's a common RFID type style antenna. If you're trying to do a filled circle, then you have to make sure it's imported in as a filled circle.
Yeah, but it can print circles, right? The
Yeah,
robotic
can.
robots in
Mhm.
that can print circles. Okay.
Yep.
Okay. Okay. Good. Okay. Any questions? You all are quiet. I'm the only person who is speaking. Well, we two are.
Yeah, no problem. If anybody has any questions, or you can also give them my contact information, Vinay, and if they want to reach out with any questions, happy to answer.
Any question? Any question, guys? No, Austin. No. Okay, so let's thanks to the speaker. Thank you, Pete, for the valuable time. So let's thanks to the speaker.
Thank you, everybody, for your time. I appreciate it.
Okay, Pete, thanks for
Okay.
joining, and then
Bye-bye.
we'll let you go. Bye.